Hello everyone and welcome to our short demonstration on how to run a CFD analysis with FLOEFD embedded in Siemens NX. FLOEFD is the front-loading CFD solution that allows you to optimize a proposed design early on in the design phase when it's easier and less expensive to modify. In this case we have a shell and tube heat exchanger consisting of a tube bundle, the shell and plates and baffles. In this demo we will investigate the influence of the baffles inside. We start a project by using the FLOEFD wizard. Here we set up the initial conditions for our project. We define a name for it, the basic unit system or modified units, and please note that we can change these settings later too. In this example we enabled heat conduction in solids. Our default fluid is water and the default solid material is steel. Let's have a look at the first version without any baffles inside the shell. The flow conditions are defined in the boundary conditions. For the hot side we assigned an inlet volume flow rate of 50 cubic meters per hour at 120 degrees Celsius. On the opposite side, the outlet side, the static pressure is 1.6 bar at ambient temperature. For the cold side we applied 70 cubic meters per hour at 20 degrees Celsius and also 1.6 bar at the outlet. The applied goals are our physical parameters of interest. In this case we are particularly interested in the pressure losses and the enthalpy differences on both sides. For this purpose these four equation goals are used. In addition to the global mesh settings, a local mesh refinement is applied to the area around the tube bundle, shown by this cylindrical section, and we can see the corresponding mesh refinement level. The project is ready to run. The meshing, which is always performed automatically, took 30 seconds on my Intel Core i7 CPU and about 250,000 cells were created. FLOEFD continues with the solver. Here we have a few graphics to show us the progress of the parameters as well as graphical previews visually. Let's take a look at some of the results. We can create multiple cut plots and we can let them move through the model automatically, defined by the corresponding planes. The surface plots are a three-dimensional plot and these show the results on the tube outer surfaces. Here, firstly for the velocity, we can see the highest velocity at the inlet and outlet area. Let's switch the display parameter to the heat transfer coefficient and we can of course observe the highest heat transfer coefficients in the same regions. And here we can see the solid temperature on the tube surfaces. The ISO surfaces show regions for a specific value of the defined display parameter. In this case we see regions with a very low velocity, which is usually not desirable for such applications. We use the flow trajectories to illustrate the flow in the hot side and in the cold side. Considering the arrows, we can also observe regions at low velocities, and in addition we see a nearly parallel flow to the tubes. We can use the parametric study to produce operating diagrams. In this case, the volume flow rate for the cold side is varied from 10 to 150 cubic meters per hour, and the results can be used in Excel, and here we can see the pressure drop and the enthalpy difference as a function of the flow rate. We use the clone function to set up a copy of our project that can be applied to a different configuration of this assembly and retains all the already defined settings. We activate the second configuration that contains some additional baffles to change the flow path through the side of the shell. And in the interest of time we are going to just move on to looking at the results. Let's change to a transparent view. And here we can see again the cut plots and the influence of the additional baffles in the current configuration. The surface plots show a somewhat more even distribution of the velocity. The heat transfer coefficient the same, and also for the temperature. Let's look at the isosurfaces again. They no longer show such a large expansion, however there are still zones with a very low velocity. The trajectories give a very clear overview of the new flow path. Although the flow path seems to be improved, we can observe these recirculation regions. These could be avoided by additional baffles, but for our current example we will leave it as it is. The Compare tool allows us to compare the results simultaneously, showing here the solid temperature on the tube surfaces, which seems to be more uniform for the version equipped with the baffles. Let's have a look at the parametric study again, and we can compare the results of the two variants. The solid lines show the variant equipped with the baffles, the dashed lines show the variant without the baffles, and we can see that the variant with baffles has a higher thermal output, but also a higher pressure drop at the same time. These investigations can be done very quickly in FLOEFD, here embedded in Siemens NX, including the family table capabilities of course. Thank you for watching our short demonstration.